Hey there, science fans. Welcome to another exciting journey into the fascinating world of chemistry. Today we're diving into the world of pH, a scale that measures the acidity or basicity of a solution. It's a tiny scale with a huge impact on our daily lives. Let's unravel its secrets. Imagine a seesaw balancing between acids and bases. On one side, we have acids. These are substances that can donate a proton or accept an electron pair in reactions. On the other, we have bases. Bases are substances that can accept protons or donate electron pairs. The pH scale measures how acidic or basic a solution is, ranging from 0 to 14. It's like a scoreboard for this chemical tug of war, indicating the strength of acids and bases. The pH scale runs from 0 to 14, with 7 being neutral. A pH of 7 is neutral like pure water, which is neither acidic nor basic. Anything below 7 is considered acidic. Think of common substances like lemon juice, vinegar, and even battery acid. The lower the pH, the stronger the acid. Strong acids can be very reactive and dangerous. Above 7, we enter the realm of bases, which are also known as alkaline solutions. These substances can neutralize acids and are often found in cleaning products. Soap, baking soda, and bleach are common examples of bases we use every day. The higher the pH, the stronger the base. Strong bases can be just as reactive as strong acids. Understanding pH is crucial in chemistry, biology, and environmental science. It helps us balance and control reactions, ensuring safety and effectiveness in various applications. Why should we care about pH? Because it affects almost everything. In our bodies, pH is crucial. Our blood has a slightly basic pH of around 7.4. Even a small shift can be dangerous. Industries rely on pH control too. Food production, pharmaceuticals, and water treatment all depend on precise pH levels. Imagine sour milk or ineffective medicines. The environment is also sensitive to pH changes. Acid rain caused by pollution can harm forests and aquatic life. Maintaining a balanced pH is vital for a healthy planet. Now, how do we keep pH in check? Enter buffer solutions. These chemical heroes resist changes in pH. They're like shock absorbers for chemical reactions. Imagine adding a drop of acid to water. The pH plummets, but add it to a buffer solution and the change is minimal. Buffers help maintain stability. This stability is crucial in many systems. From our blood to laboratory experiments, buffers ensure that pH stays within a narrow, optimal range. What's the secret behind buffers? They're made of a special duo, a weak acid and its conjugate base. This pair works together to neutralize any added acids or bases. Think of it like a dance. When an acid enters the solution, the conjugate base steps in to neutralize it. When a base arrives, the weak acid takes the lead. This dynamic equilibrium keeps the pH stable. It's a delicate balance, but buffers are masters of maintaining it. Section 5. Acetic acid and acetate, a buffering duo. Let's meet a famous buffering pair. Acetic acid and acetate. Acetic acid is found in vinegar, giving it that tangy taste. When acetic acid dissolves in water, some of it loses a hydrogen ion, forming acetate, its conjugate base. Together they create a buffer solution. If you add acid to this buffer, acetate will absorb the excess hydrogen ions, and if you add base, acetic acid will release hydrogen ions to counteract it. Section 6. How buffers work, a balancing act. Buffers are all about balance. They play a crucial role in maintaining the stability of pH levels in various solutions, which is essential for many chemical reactions and biological processes. They maintain this balance by controlling the concentration of hydrogen ions in a solution. This delicate equilibrium is vital for processes ranging from industrial manufacturing to the functioning of our own bodies. Remember, pH is a measure of hydrogen ion concentration. A small change in pH can have significant effects, which is why buffers are so important. When an acid is added to a buffer, the conjugate base gobbles up the excess hydrogen ions. This reaction helps to neutralize the added acid, preventing a sudden drop in pH. This prevents a drastic drop in pH, ensuring that the environment remains stable and conducive for the intended reactions or processes. Conversely, when a base is added, the weak acid releases hydrogen ions to neutralize it. This action helps to counteract the increase in pH that would otherwise occur. This stops the pH from skyrocketing, maintaining a stable environment. The buffer system is constantly working to keep the pH within a narrow range. It's a constant push and pull, ensuring that the pH remains stable. This dynamic balance is what makes buffers indispensable in both scientific and everyday contexts. Section 7. Buffers in action, real-world wonders. Buffers are essential in countless applications. In our bodies, the bicarbonate buffer system regulates blood pH. It's a matter of life and death. Laboratories rely heavily on buffers. They are used in experiments, calibrating instruments, and growing cells. Without buffers, results would be unreliable. In agriculture, buffers help maintain optimal pH levels in soil. This ensures healthy plant growth and better crop yields. Section 8. Mixing your own buffer. A step-by-step guide. Want to make your own buffer? It's like following a recipe. First, choose your desired pH. Different buffers work best at different pH ranges. Next, select a weak acid and its conjugate base that match your desired pH. You'll need to calculate the correct amounts using the Henderson-Hasselbalch equation. Don't worry, we'll cover that next. Once you have your ingredients, dissolve them in water and adjust the pH if needed. Voila! You have a buffer solution ready to resist pH changes. Section 9. The Henderson-Hasselbalch equation, predicting pH. The Henderson-Hasselbalch equation is a handy tool for calculating the pH of a buffer solution. This equation is fundamental in both academic and practical chemistry, providing a bridge between theoretical concepts and real-world applications. It looks like this: pH equals pKa plus log of the ratio of the concentration of the conjugate base to the concentration of the weak acid. This formula might seem intimidating at first glance, but once you break it down, it becomes much more approachable. Don't let the symbols scare you. Each part of the equation has a specific meaning and purpose, making it a powerful tool in predicting pH levels. pH is what we're calculating. It's a measure of how acidic or basic a solution is, and it's crucial in many fields from biology to environmental science. pKa is a constant specific to the weak acid. It represents the acid dissociation constant, a value that helps us understand the strength of the acid in question. The concentration of the conjugate base is represented as A-, and the concentration of the weak acid is represented as HA. These concentrations are key to determining the pH of the solution. Let's say we have a buffer with a pKa of 4.76 and equal concentrations of acid and base. This scenario is common in many laboratory settings and helps illustrate the equation's practical use. Plugging these values into the equation gives us a pH of 4.76. This result shows how the equation can predict pH accurately when the concentrations are known. See, math can be fun. Understanding and applying these concepts can be incredibly rewarding, especially when you see the results in your experiments. Buffers are the unsung heroes of chemistry. They play a critical role in maintaining the stability of pH levels in various environments. By maintaining stable pH levels, they keep our bodies functioning, our experiments accurate, and our environment healthy. Without buffers, many biological and chemical processes would be disrupted. So, next time you encounter a buffer, give it a nod of appreciation. It's a small but mighty component in the world of chemistry. It's working hard to keep things in balance. Whether in a lab, in nature, or within our own bodies, buffers are essential for maintaining equilibrium.